Hi, this video we're going to cover trees in Python, and just to go through a little background before we actually get started on this. So I'm going to bring over the book that I use in one of my classes. It's a PDF open source book. So now we've studied linear data structures like stacks and queues and have some experience with recursion. We're going to look at a common data structure called a tree. Trees are used in many areas of computer science, including operating systems, graphics, database systems, computer networking. If you ever think about when you go to open up a file, I'm going to do this from here, open up a file. This is kind of like a tree here. Okay, say for example, my D drive. There, D would be the root. Active Presenter is a software package that I use. Would be the OneNote. All these folders in here, and you can go deeper and deeper into here on all these. So this is similar to a tree, or is a tree. Okay. So notice that you can start at the top of the tree and follow a path made of circles and arrows all the way to the bottom. At each level of the tree, we might ask ourselves a question and then follow the path that agrees with our answer. For example, we might ask, and what they're using here, botanical cousins, so common in there. Okay, so that's what they're talking about. Is this animal a chordate or an arthropod? If the answer is chordate, then we follow that path and ask, is this chordate a mammal? If it's not, then we are stuck, but only in this simplified example. When we are at the mammal level, we ask, is this mammal a primate or a carnivore? And then we can keep going with this and looking down. So let's, I think I've got a picture of this here. There we go. Okay, so this is the animal kingdom all broken down, and we can take it all the way down until we get down to the actual one that we want here. Okay, so then the second property of trees is that all of the children of one node are independent of the children of another node. So for example, the genus Felis has the children Domestica and Leo. The genus Musca, well, I can't pronounce these names because I'm not a biology person, also has a child named Domestica, but it is a different node and is independent of the Domestica child in Felis. So this means that we can change the node that is in the child of Musca without affecting the child in Felis. Okay, so let's go on to another one. Maybe I can pronounce the words in this one. Okay, so this one here is showing Unix file system. So third property is that each leaf node is unique. We can specify a path from the root of the tree to a leaf that uniquely identifies each species in the animal kingdom. So they were still back on that. So let's do another example of a tree structure that you probably use every day, a file system. In a file system, directories or folders are structured as a tree. Figure 6.2, which is the one up here, illustrates a small part of the Unix file system hierarchy. So I'm not going to go through all these, kind of shows you here how that's broken down, and you can still do that. Windows would be the same way. On how it's broken down by folders and then the documents inside the folders. And then this is an HTML one, how it's broken down, and they give an example of it here. You have HTML, you have the head, the body. The head has meta and title. The body has UL, H1, H2, and so on there. So let's look at the vocabulary and definitions. Okay, so here's some of the vocabulary. A node is a fundamental part of a tree. It can have a name, which we call the key. A node may also have additional information. The edge, an edge is another fundamental part of a tree. An edge connects two nodes to show that there is a relationship between them. The root of the tree is the only node in the tree that has no incoming edges. A path is an ordered list of nodes that are connected by edges. Children is a set of nodes that have incoming edges from the same node are said to be the children of that node. A node that is the parent of all the nodes is it connects to with outgoing edges. So we'll go down here and look at this. Here's an example here. This would be the root. This would be the children of the root node. This would be considered a parent that has 3 children, and then these are the nodes that those are connected to. Okay, so then some more of these. Sibling nodes in the tree that are children of the same parent are said to be siblings. A subtree is a set of nodes that and edges comprised of a parent and all the descendants of that parent. A leaf node is a node that has no children. The level of a node, n, is the number of edges on the path from the root node to n. To kind of give you an example of level, if you think about when we talked about binary searches and how it halved everything, and you could, if you had 1 million items in that are sorted, it would only, the maximum number of comparisons you'd have to make to find what you're looking for is 20. Similar to what we're going to do later in another video is a binary search tree, which sets everything up in order so that if you're looking for something, you can go down the path, and 1 million items, then the longest you'd have to go would be 20 because that's the depth of the tree. So that talks about the level, and then the height of a tree is equal to the maximum level of any node in the tree. Okay. So then that was the definitions then. With the basic vocabulary now defined, we can move on to a formal definition of a tree. So definition 1, a tree consists of a set of nodes and a set of edges that connect pairs of nodes. A tree has the following properties. One node of the tree is designated as the root node. Every node, n, except the root node, is connected by an edge from exactly one other node, p, where p is the parent. A unique path traverses from the root to each node. If each node in the tree has a maximum of 2 children, we say that the tree is a binary tree. Figure 6.4 shows a tree that fits definition 1. Okay. We'll look at that here in a second. Definition 2 is a tree is either empty or consists of a root and 0 or more subtrees, each of which is also a tree. The root of each subtree is connected to the root of the parent tree by an edge. And here's figure 6.5, kind of shows us with the root and then 3 subtrees. Okay. Using the recursive definition of a tree, we know that the tree in figure 6.5 has at least 4 nodes. Since each of the triangles represents a subtree, must have a root. It may have many more nodes than that, but we do not know unless we look deeper into the tree. So this is one of the things that we'll be able to do with this, is to be able to use recursion to search through this, because each node is in fact also a subtree or a tree of its own. So this subtree 1 here can be considered a tree of its own with the nodes that are underneath it. Implementation. Keeping in mind the definitions from the previous section, we can use the following functions to create and manipulate a binary tree. A binary tree that creates a new instance of a binary tree. Get left child returns the binary tree corresponding to the left child of the current node. Get right child returns the binary tree corresponding to the right child of the current node. Set root val stores the objects in perimeter val in the current node. Get root val returns the object stored in the current node. Insert left creates a new binary tree and installs it as the left child, and insert right creates a new binary tree and installs it as the right child. So this book does a list of lists, which I really do not like at all because it uses nested lists to create these. And if you look at this, you can see how the brackets are in here, and it makes it real complicated for me, in my opinion, to look at this. So we're going to skip over this, and we're going to go to nodes and references. So what we're going to do is we're going to create a binary tree using similar instance of like a linked list. Okay, so we're going to start working on this. Here, let me get things set up here. Okay, so we're going to start with a blank file here. And the first thing we need to do on here is we're going to create a class node. We're going to have our init and pass in the value that we want to store into the node. So self.value is going to equal the value. And then we need to set up the right and left. So self.left is going to be equal to none because it's not pointing to anything yet. And self.right is also going to be equal to none because it's not pointing to anything. We don't have any other nodes on there yet until we actually do this. Then we want to set up our binary tree class. Okay, so every time we're going to add something to this, we're going to actually create a separate tree and then attach it in there where it needs to go. So in this case, our binary tree, the init, we're going to pass in a root value. So self.root is going to be equal to node of root value. Okay, so we're going to create a node. The value that we pass in is going to be stored in our value in our node. Next thing we need to do is be able to insert values for our left and right of this. So we're going to do an insert left, passing in the current node and the value. So if current node dot left is none, then current node dot left equals node value. Okay. So if it's none, then our current left is going to be a new node, and we pass the value and store that in there. Else, new node is going to be equal to node value. New node dot left is going to be equal to current node dot left, and current node dot left is going to be equal to new node. Okay. So if there is a current node left already, then we need to put that in there on the left side of the current node, or of the node that's on the left there. So then we're going to do the same thing with right. Oops. So this one then, if current node dot right is none, then current node dot right equals node value, else new node equals node value. New node dot right will be equal to current node dot right, and current node dot right equals new node. So let's go through this and kind of explain it a little bit better here. Okay, so we got to create our node. Both places we do, whether it's current node dot right equals the new node, or we just created and stored into new node on here equals node value. Okay, so if there's already one in the right position, then our new node right, that's the new one that we have, is going to be equal to our current node dot right. And then our current node dot right is going to be equal to new node. So it gets put in there in the right place there. Okay. Now, once we have them inserted, on there, I'm going to open up something else here real quick, and we'll see if I can get this stuff working here. Do another tree here, another one I'm going to look at. Because the other things we need to be able to do is to be able to get the values off of here. And we can do that with a print. But we also need to be able to get these out of here. So we're going to do a get right, passing in self. And then what we're going to do is return self dot right. And then do the same thing with self dot left. Okay. So I'm going to stop with this. And then what we're going to do is we're going to do a little, let's go ahead and save this. And I'll do a new folder here and call solution, and that's what I'm going to save it in. I'm going to save this as BT, capital B, capital T, .py for binary tree. Okay. So then what we're going to do is a little example program. From BT, I'm going to import node, and then from BT, I'm going to import binary tree. So in here, what I'm going to do is I'm going to do tree is going to be equal to binary tree and pass in the value 10. Do a tree dot insert left. I'm going to pass in tree dot root 6. I'm going to do a tree dot insert right, pass in tree dot root 14, tree dot insert left again, passing in tree dot root dot left 3, tree dot, we haven't done these yet, print in order tree dot root. I'm going to do a print dot, tree dot print pre-order tree dot root, and then a tree dot print post order tree dot root. Okay, let's go back over to here. We've got to put these in here now. So the other things that we need on here is ways to be able to print out. There's 3 different ways to print out: in order, pre-order, and post order. So let's do the pre-order first. Or the in order, sorry, in order. Self and node is what we're going to be passing into that. We're passing in the root on each one on our test program. So now we're going to do if node. So if there is a node, this is what that's saying. If it's not equal to none, it's something else. Self.print in order node.left. Okay, and then print node.value. And then self.print in order node.write. Okay, so this is doing recursion here. So what happens is, if there is a node, then it's going to call print in order, passing in node left. So then it goes back up again. If there's a node, it will come down and call print order node.left. So it's going to keep going left, 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 left. And then as soon as it hits one where there is no node again, it will print node.value and then call off the stack the next the previous one and go back all the way back up again. Okay. When it gets to the last one, then it comes down and calls print in order node right, and then does the same thing on the right side until it gets down to the last one and then backs back out again. Okay. So let's do the next one then. Next one is the pre-order. In this one, I'm going to do this one just a little bit different so you can see different ways of doing this. If node is none, return. And then print node.value. Oops. And then self.print pre-order node.left, and then self.print pre-order node.right. Okay. So this one does it a little bit different now. It prints the value. If there is a node, it prints the value, then it goes left, comes back up. If there's a value, it prints it. Okay. Then it goes left, prints it, then it goes left, prints it. When it runs out on the left side, okay, it is back all the way up. So then it's going to hit this one here, which is the next one, which then is going to go to right, print it, check left again, all the way down through it, and then come back up to the right and go right. So it's going to go left all the way down, then back up to the current node, and then right one, and then check to see if there's any lefts and press all the lefts and come back up, and then it will come back and do all the rights. Okay. So then the last one then is the post order. Oops, misspelled that there. I'm gonna get that fixed. There we go. Okay, so in this one, then I'm doing the same way as I did this one. So if node is none, return self.print post order node.left self.print post order node.right, and then print node.value. Okay, so this was a little bit different. Okay, notice up here, first one does all the lefts, then prints back out through again, and then all the rights and prints back out through again. What this one does, or I'm sorry, prints all the lefts, goes all the way down to the bottom of the left, and then comes back up and prints, then goes to the right, and then gets to the left again on those, it comes back. This one prints the value, then goes left and prints left print, left print, left print, and then right print, right or right, and then left, all the lefts and then rights. Okay, so it keeps going back and forth that way. And then this one goes left all the way down. Okay, then when it runs out, it goes to the right and then back left and then prints. Okay, so there's different orders. So I'm going to go over here now. I'm going to go ahead and save this so I don't forget. Go back over here now, and I'm going to print out a message on each of these. Do in order, and do the in order, and then pre-order, and then post order. Okay, so let's go ahead and run this. Oh, I didn't save it. So bttest.py. Save that. Okay, so okay, I think I know what I did wrong. Let's see here. Yeah. Okay. Print in order, and the error was on the in order. Okay, so I'm not seeing the error. So on the line tree.print in order tree.root, it's saying that it doesn't, I have no attribute print in order. But it's right there. Oh, there we go. That lowercase o on there, and that's I think what's going to do that. Let's check and see here. Yep, there we go. So that worked. Just one little bitty error there. Need that capital O on there. Okay, so here's the in order 3, 6, 10, 14. Okay, so that's the order. Then the pre-order 10, 6, 3, 14, and then the post order 3, 6, 14, 10. So a little bit different on the orders, and so depending on what application you're doing would depend on what order you're going to print them out. So I hope this helps out on how to create binary trees. Next video I'm going to do is going to be on binary search trees. Bye.